uh, Clap decided to fail at the last minute. So I need to write down some things at the very beginning. We said that we wanted to revise how we design a circuit. So um, the topic basically is finite state machine. All right. So we said that the task is to design a counter that goes 1, 3, 2, 1, 3, 2, 1, and so forth. So the first thing that we're going to do is write these down in binary. So 1 is 0, 0, 1, 3 is 0, 1, 1, and 2 is 0, 1, 0. Well, actually, we don't need the first digit. That just going to complicate our work.
Sir Fraser,
Yes.
you know, we can not seeing a thing, sir.
Go to the next diagram, Fraser. So this, the one that you're looking at, that you're not seeing anything, you're just seeing somebody in a pink shirt. That is for the where we're going to go to the computer. But right now, I'm just writing down some things on a board. So.
All right, sir. No trouble, no trouble, no trouble.
All right. So. All right. Now, help me here. But remember the truth table for a JK flip flop.
I have a good idea what it look like.
All right. So you see this thing here now. If the present state of the JK flip flop is a value, what is the next state going to be when J and K are both 0? Anybody remember? This table is called the characteristic. Sorry, excitation table.
Oh, the excitation table.
But remember this.
Yeah, sure, you're in front of the camera. I just your pink sleeve, man, see now.
Go to the next Darren Fraser.
All right, cool. Let me see. Oh, copy.
You see it now?
Yes, sir. Trouble, no trouble. Right.
All right. So the JK is a version of the set reset flip flop. And what we know about with the set reset flip flop when the set is 1. What set mean, by the way? All right, let's take it from there. So you have to treat this like a Pentecostal church. You have to talk to them. Then I talk to you. You don't do that, then this is not an information passing session. This is a problem solving session. So we have to talk to each other. So if you don't know the answer to the question, please say I don't know, so that we know where to go. All right, so let me ask the question again. And then I need to hear whether we know, don't know, or like X don't care. So I was asking about if you had a flip flop. Remember those things? Let me these things here. You remember these things here, the flip-flop?
Yes, sir. Yes, sir.
All right. One was set and one pin was reset.
Yeah.
So I was asking, when the set pin is 1, what
Yeah.
happened to the output?
I think that'll be 0, and sir.
No.
No, it'll be 1.
1. Set the
Yes, sir.
output, whatever the this X mean don't care. Whatever the output is, you're going to go to 1. So what about reset? 0.
0.
Memory. When both inputs are 0, the flip-flop is said to be in the state of memory. What happens when you're in a state of memory?
0.
No. No.
Whatever it's set to.
Huh?
Whatever it's set to.
Whatever
1.
it is, it's going to remain that. Remember, say this means don't care. X means 0 or 1. So you don't care. So they call it the don't care condition. So whatever it is, whether it is 0 or 1, it remains at 0 or 1. That's memory. Whatever it is, you retain whatever the value it is. Set, reset, it goes to 0. Set, it goes to 1. What about toggle now? Not seen? Or the same thing again?
I don't care as well.
Sorry, yeah. Yeah, the toggle state now.
I don't care as well.
All right, so you're going to change from what is there to the next. So if it is 0, it becomes 1. If it is 1, it becomes 0. All right, so memory, whatever it was, it stays like that. Reset, when reset is a 1, it's going to, output is going to go to 0. When set is a 1, the output is going to go to 1. And toggle, the output is going to change to the opposite of what it was. And this table now that we have here is called the excitation table. Now, to do our little design here, 1, 3, 2, 1, we need to rearrange this table. We don't want the excitation table. We need what is called a characteristic table. So let me, we're going to need the excitation table. So let's bear that in mind. I was writing these things first to establish something, and then we can proceed. All right. So we have excitation table, which is this table here. And well, it's easy for my old brain to remember, because all I have to remember is reset is 0. Reset means I go back to 0 and everything is false. All right. So now we want to write down the sorry, somebody else need to get let in. All right, so we want to do now the characteristic table. So the characteristic table turn this table backward. So if we are at Qn I want to go to Qn plus 1, the next state. So this is the present, if we are presently at this value. And we want to go to this next value. What values of J and K do we need? So now, if we are going to set up our table as before, and we're going to work it out. So now, if we go back over here, consider this is 0, 0, 1, 0, 1, 0, 1, 0, 1. If we are presently at 0, remember now, look over here, Qn is 0, and the next state is 0. What values of J and K do we need for that? So if we are presently at 0, now let me just fill in these here, 0, 1, all right, if we're presently at 0, so these are the zeros that we have at present. And the next state is 0. So this is one case where the presently at 0, the next state is at 0. And let me find the next one in the table. Presently at 0, the next state is 0. There is no other there. So presently at 0, and the next state is 0. And down here, presently at 0, the next state is 0. Let's do some rough work. What values of J and K do we need? Presently at 0, next state is 0. What value of J and K causes that? Well, in this particular case here, up here, J would be equal to 0. And K would be equal to 0. But for this case now, presently at 0, and the next state is 0. What values of J and K cause that? 0 and 1. So these are the two conditions that we have here. That if we are at 0, so in this table, if we are at 0 and remain at 0, the two conditions that we have here, J is 0 and K is 0, or J is 0 and K is 1. So how we list that in the table is that we say J has to be 0 and K we don't care because it's either 0 or 1, we don't care. So write it like this, 0, don't care. So now let me check and see if anybody listening don't reach understanding yet, just a listen. And go back to the rough work here. If I'm presently at 0 and the next state is 1, what values of J and K do I need? Presently at 0, next state is 1. So if we go back over to our excitation table, presently at 0, next state is 1. That is one case. And the next one here is down here. Presently at 0, next case is 1. Everybody see what I'm talking about?
I really understand. I really understand. Please.
J is on, sir, and K is don't care.
All right. So let's write only two situations. Presently at 0, next case is 1. So J is 1, K is 0. Presently at 0, next case is 1. The next thing is 1, 1. And you are saying that in this particular case, J is 1. J has to be 1. And K is don't care. That is true. All right. What about now? Presently at 1, next case is 0. Presently at 1, the next state is 0. Presently at 1, next state is 0. What are the J and K values? Presently at 1, the next state is 0. So that's what is the J and K value? That's 0, 1. All right, presently at 1, the next state is 0. Presently at 1, the next state is 0. So that will be J equal 1 and K equal 1 as well. You follow what I get again? Yeah. So J is 1 and K is 1. Right. So therefore, we're going to write down this as in our table. We don't care what J is, and K is 1. So by the symmetry of the table, we can write down the last one is don't care 0. But anyhow, let's check it. Presently at 1, and the next state is 1, and we want to find the J and K values. Presently at 1, next state is 1, what value of J and what value of K. Presently at 1, next state is 1. Present value is 1, the next state is 1. So it would be J is 0 and K is 0. Find the next one. Presently at 1, the next state is 1. So this is here, where we have J is 1 and K is 0. So K is 0 and J is 1 here. Like we said, by the symmetry of the table, we would expect that. So this characteristic table is our starting point for the problem. All right. So if you're not writing down anything else, could you write down this, please? Because I need to refer to this. My memory not all that wonderful. I'm gonna put it up in front of us. So somebody write it down. So this is our starting point where we want to go. All right, somebody write it down. All right. So now, so to get the counter that we want, we have to set up an excitation table. Now, each of these, the binary value for each of these, the maximum number of digits that we need is 2. So therefore, we are going to need 2 flip-flops because it's 1 flip-flop per value. So 2 flip-flops. And we're going to set up a big three person. going to set up this table now. And what we are going to set up is that we are going to write down all the possible states that we can have. Zero, zero, 0, 1, 0, 1, 1. And so we set the present value of the two placeholders is 0, 0. And the next, we want to write down the next, and then we're going to use the characteristic table to fill in what values of j and k will cause the change. All right, I'm going to start at the base of the table. And so if I'm at 1, 1, let me just write it down here. 0, 1, 1, 1, 1, 0. If I'm at 1, 1, presently, what is the next state that I'm going to go to?
2, sir.
If I'm at 1, 1, I'm starting at the base of the table. If I'm at 1, 1, and what is the next state that I'm going to go to? If I'm at 1, 1.
1, 0, sir.
1, 0. So would write it 1, 0. If I'm at 1, 0, what is the next state that I will go to?
0, 1.
0, 1. If I'm at 0, 1, what's the next state that I go to? 1, 1. And 0, 0 does not appear in my what I want. So therefore, I don't care. Some people when they design, they put 0, 0. They will put, if it goes to 0, 0, then they put a state. There, that's to make it go to 1, 1. I don't know if you understand what I mean. 0, 0 doesn't appear, but they would make sure that if something happens and go to 0, 0, then it will go to the state 1, 1. We can do that, or I'm going to put no K for the time. Everybody understand what we're saying with the 0, 0? You can't put anything there basically. So I'm putting don't care. All right. So now, in conjunction with our characteristic table, if I'm presently at 0, I'm going to 0, j and k are these values, and so forth and so on. What I'm going to do now is say, if my present value is 0, let me start here again at the bottom. Present value is 1, next value is 1. What values of j and k do I need? If I'm presently at 1, this is my value here. And then this is the next state here. If I'm going from 1 to 1, what values of j and k do I need? Refer to the table.
Don't hear 0.
Presently at 1, that's why I tell you what I'm write it down. So we can just tell over here circuit. Presently at 1, next state is 1. What do I need? Okay.
Don't care for J and 0 for K.
All right. So now we're going to fill in for this one. For B now, if I'm presently at 1, I'm going, next state is 0. Presently at 1, next state is 0. K is 1. All right, so let me make it clear. All right.
Sir,
Mm-hmm.
I have a little issue, sir.
Mm-hmm.
And my timetable it says that I have class at 3, right?
Mhm.
And I said that my other class ends at 3 with Mr. Isaacs. Just know
Mhm.
that I explained to the man say, yo, you know, say me have a class and now before me start talk, he want to say him can't deal with that right now. And I try to explain to the man say, for my timetable, this is say him go ahead and switch the time for film class. I know they affect this class. I don't know how him get them the powers if we go ahead and do something like that. Yeah, but at that, me there in the class and me I try, me tell him say me have a little issue. Me not able to say one sentence good, the man start basically shut me up like a some boy thing.
Um, I am not sure what my response to that is.
Your boy say Fraser. Tandem, you know a thing already, Tandem.
Let us proceed.
All right, sir.
Can I say
Yeah,
hush?
man, let us proceed.
Tired of this man now, though, man.
Nah, man, you know a thing, man. Just make it run, man. All right, Sir Fraser, your turn.
Yeah.
Hold on, you know what? Sorry, sir. You know why I say it, sir? Because last class, the man give an assignment. What do within the class time? The last hour of the class, it should have been into this time. Now, if me not did forget that, then now, me might get a 0. And him have a good thing for love, give me 0.
Especially you because you love terrorizing the man.
Why? So I just not put up with foolishness. Everybody is
Yeah,
normally quiet and
no,
ask.
but hear what happened. Sometimes you have to pick your fight. Yeah?
Yeah, man, you're true, man. You have to pick a fight, them, man. You know that, Tandem.
Yeah.
You know a thing already.
It is my neighbor who said sometimes you have to kiss ass before you can kick it.
You kick it still, man, but you know a thing already, Tandem.
All right. So we are here. 1 to 0. So we want to know A is 1 and the next state is 0. So what are the values of J and K that we need? 1 to 0. So that will be down here 1. And then now 0 to 1. 0 to 1. What we need for that one? 1 for J, don't care for X. So 1, don't care.
Sir Fraser, sorry, Sir Fraser. You record this session?
One member of the class are recorded. Conroy record.
Ah, perfect.
All right. 0 to 1. 0 to 1 is which one again? And this one is 1 to 1. And this one we have don't care, so we're just going to put don't care. So this is our table. All right. So now the circuit that we are going to put together now is going to have 2 flip-flops. All right. So the output of the first flip-flop we're calling A. Output of the second flip-flop we're calling B. And it's going to be a flip-flop with a clock. attached. Clock is an A stable. And so we want to find out what should we input as JA, KA, JB, and KB. All right. So somebody need to write this up because I'm going to leave the board now and go to the computer. So this circuit here was 0, 1, where go? Sorry. 1, 3, 2, back to 1. All right, so we need this. We're going back through this. It's not this that we want to do, but we have to understand this to be able to design a circuit to control whatever process it is that we want to control. We have to understand the whole finite state process. All right, so you go from one state to the next, to the next, to the next, and rotate like that. So we want to be able to discuss how we use this very same thing. So to do it. So we have to define our states, and then we're going to make up an excitation table just like this. Somebody write off the table already? Church drop asleep. Yes, somebody say amen. No? Alright. Alright, so we're going to switch to the next screen now. So just bear in mind the following. Presently, we have this state, and then we have these values for J and K, and what we are going to be doing is simply this now. Each of these, this is our input to our truth table. We ignore the next state for now. So we ignore the next state. So this is the input to the truth table, and this is the output for J. So this truth table is here, and this output J. What is J going to be equal to? Well, so just allow me to just go to the computer. And if you have a computer, you can just go to your computer, please. All right, so I have up electronic workbench. And I'm going to take out the JK flip-flop that I need. So I need 2. I'm going to need an ACE cable. Too fast, change it to 1 hertz. So hopefully we can see what is going on. And we're going to connect up that. All right. So now we have the truth table. Like I said, I hope you all wrote it down. And we don't really need to do this for this basic one, but we're still going to do it. I took out a 7-segment display. And let me take this back out. Now, in multisim and in electronic workbench and those things, we have a logic analyzer. So if we open it, this is what I want to get at. So I'm not seeing it. Logic converter is not working. Not coming up. Let me check it out again.
Sir, someone waiting to the team.
Uh, I don't know what is going on here. Well, we have to go switch to plan B. Anybody else have a logic converter? Can go to your screen. Pull it out. Anybody have MATLAB open? I mean, not MATLAB. Electronic workbench open. No. Somebody else open it. Because I wasn't planning to do it by hand, but if I don't know what is the matter with this.
Sir, try close that open it back all over and sit down.
Yeah, let me do that. Alright, so let me open it back. Alright, so I'll pull it out. So when you click and double click on the logic converter, this is what comes up. This screen that I'm highlighting here is what comes up. All right, and we need 2 inputs to the screen. 0. All right. Now if you look at the JA column, I know what we would write down immediately, but I just want to demonstrate maybe there's somebody who don't know how to use the logic converter software, so we'll just demonstrate it. All right. What you have in the first column, the reason I'm asking you this is because I need to know so I don't drop asleep on me. What do you have in the first column for the JA?
Don't care, sir.
So when you click, you can just type in X. What's the next one? 1. Type in 1. And then X and X. All right, now this is supposed to simplify and give me a 1. So what you'd go to simplify. So if you look on the right hand side, look on the right hand side over here, you will see that it has, if you have a set of gates and you want the truth table, if you have the truth table and you want to set the Boolean expression, if you have the truth table and you want the simplified Boolean expression, you click on whichever one you want. You have a Boolean expression, you want the truth table, you have a Boolean expression, you want the circuit. And you want the circuit with only NAND gates, you click. So I want the simplified circuit, which we expect is X, 1, X, and X. So I expect it to be 1. And the result is here. So the input to my JA is going to be 1. So just make a note of it, everybody. I'm writing it down. JA equal 1. But you could look at the table and say, is X, which can be 1 or 0, and is X1, XX, so that can be, the whole entire table can be just replaced by 1s. So therefore, all right. So we could try KA now. So KA, the first one is X. What's the second one? So we type in X. Also, we suppose you can double click on it and it just change it. But anyway, all right. It's now so the next one is what? 1, and the last one is 0. And so we're going to simplify that, and we get B bar. So JB is equal to B bar. Please write it down. Sorry, not JB, KA. That was the row we're looking at. JB, we're not going to simplify it, is XX1X. So what that would work out to?
One.
1. And so KB, writing down what that is equal to. So KB now. The first one is X. What's the second one?
0, sir.
0. And the next one is
X.
X. And the last one is
1.
1. And so we're going to simplify that, and that is just A. So KB equal A. So let's work out our, so we have our circuit worked out. JB is 1 because it's XX1X. So we're going to go back, get our 2JK flip-flop. So this is A. Let me write it down. All people tend to forget these things. Miscellaneous text. So up here, so it's K. And this one is B. All right. So now, well, before, let me just deal with the clock. The 1 hertz. All right. So JA is 1. So we can do one of two things. We can just put a VCC, which is, let me see how much volts this is. Supposed to be either 5 or 12 volts. All right. We're assuming say is 5. It won't kill anything. So we have JA is 1. And KJB is 1. And then now we have KA is not B. So this is not B. This is B. So this is B. The output here is B. Let me just do that. And this output here is A. So JKA is not B. And KB, where was A? Um, to see if this thing is working properly. I can never remember which one to panic the 7-segment display, but there's these two are the first two. Let me try the first. Try the first. Hope we don't need anything else. Yeah. Try something else. Not sure about something. All right, so I'm going to switch them around and see. All right, so see if I have to connect up. Let's check out the right one, them do. We'll connect up these here. All right, but while I'm sorting out this, so this thing here is the circuit, and you would connect it up and then check if it is working or not working. Well, it's not working. And I think the reason why it's not working is because of these flip-flops that I chose. Should have chosen the other one. You have ones that don't need this one here. But like I said, somebody can try it and get it sorted out. Because there's one other thing that I want to talk about today. I was just demonstrating how the circuit is going to work. So I want to do a bigger circuit, and we tried to simulate it before. So I'm not going to spend the time troubleshooting this to get everything working. All right, that everybody know where I want to work out one other problem before, and then we can go troubleshoot. Let's see if this. All right. So everybody get the general gist of the circuit and what it is that we are required to do to design a circuit. All right. So I want to go to something else. So going back to the board and design a bigger circuit. And then so that the next class we talk about what we actually need to be able to do. So oh. All right. So we're going back to the board. Back to the next Darren Fraser. Alright, so here is what we want to talk about now. So we want to design a circuit. Does an input I. When I equals 0, the circuit counts 1, 2, 3. When I equal 1, the circuit counts 2, 1, 0. That is our problem that we have. Everybody read and understand the problem? Remember, says me one in the house, so yeah, I'm like a madman talking to myself. Yeah. All right, so what we are going to do is that we are going to have a table with our input I, the present value of A and B, the next value, and then what J, what K, uh, all right. So this would be present input next and JA and KA. So you have the input I, present value, next value, and the J and K values that you have associated with it. So I'm going to go ahead and fill in all the possible values through table style. Alright, so I'm filling in all of the values, and then now I'm going to fill in my next state values. So now, this is the truth table. My input, present state, next state, and the J and K values that we cause that. So now, if I equals 0, and we are presently at 0, 0. If I equals 0, we don't have 0, 0 in this configuration when I equals 0. So therefore, I'm going to put that I don't care. So just all right. If I equals 0 and presently at 1, if I equals 0 and I'm presently at 1, then the next state that I go to is 2. Agree? And 2 is 1, 0. Let me just write, this is 0, 1, or 1, 0, or 1, 1. So 1, 0, 0, 1, 0, 0. So I'm presently at 1 when I equals 0. The next state that I go to is 2. So I fill in 1, 0. And if I equals 0, and I'm presently at 2, the next state that I go to is 3. So I fill in, if I equals 0 and the present state is 2, then the next state is 3. So I put in 1, 1. And if I equals 0 and the present state is 3, then I'm going to go back to 1. So I put 0, 1. All right. Wait a little bit. How come only I'll leave left out one? All right. Now if I is 1 and the present state is 0, I is 1 and the present state is 0. I is 1 and the present state is 0. Then the next state that I'm going to go to is 2. So I'm filling in 1, 0. If I is 1 and the present state is 1, then the next state that I go to is 0. I is 1, I equal 1, and the present state is 0, 1, then the next state that I go to is 0. So 1, 0, 1, next state I go to is 0, 0. I is 1 and we are 2. I equal 1 and we are 2, and the next state that I go to is 1. Oops. Sorry, ladies and gentlemen, the phone, no, it's moving. We don't know how we touch. But it left the meeting. Get vexed and left the meeting. So let me just knock back. Um, 99. And let myself back in. All right. So everybody go back over to the board. All right. So the last two now. When I equal 1 and I'm at 1, 0, is 2, then I go to 0, 1. And when I is 1 and I'm at 1, 1, there's no 3 inside here, so I will put down here. All right. So now, if I'm at 0 and I go to 1, what are the values of j and k that will assist me with that now? Remember, so we have to write it out because I can't really remember them without I can kill myself because I want to write it up on a sheet of paper. Of course, I'm speaking to myself.
To repeat?
Yeah, man. Which part? Where do we meet there?
Yes, sir. So you're going A to in A?
0 to 1. What j and k give me 0 to 1?
1x, sir.
1x. 0 to 0. We just feel everything.
0x.
What that?
0x.
0 to 1.
1x again, sir.
1x again. 1 to 0.
x1.
1 to 1.
x0.
1 to 0.
x1.
1 to 1.
x0.
Alright, so B now.
Done.
1 to 0.
1. Repeat, sir.
1 to 0.
x1, sir.
0 to 1.
1x.
What that?
1x.
1x. 1 to 1.
x0.
0 to 0.
0x.
1 to 0.
x1.
0 to 1.
1x.
1 to x. Oh,
1 to 1.
don't care.
No.
Alright. So now. So this is the truth table. And then we would ask for multisim to simplify it. Days gone by with second normal, but we're not into that.
Sir, we know. Oh, there it is.
Alright. So now.
Sir, can you put back the camera on the board for a sec, please?
But then?
The phone on the board for a sec.
Oh, okay.
All right, sir. Thanks.
So we are going to simplify, and we have three inputs now. So be careful now. What the problem? We have I, A, and B. So my I is the first one that they call it A. So we're going to have these three. Now the first one is I. What we call in B is A, and what we call in C is B. So when we translate in our table to what is here, we have to be very careful. So now, what are the values that we have for the JA column? And then all right, so we want to simplify that. So that's C that is there. So our JA is not C. Our JA would be B. Remember now it's IAB. Although they have A, B, C, our first one is I, second one is A, next one is B. So JA would be B. KA. Simplify. And so our KA would be that's C bar, which is B bar. KJB. So our JB would be A. And the last one anybody else who have it?
X1, X, 0X, 1XX.
All right. I'll simplify that. And that is A bar. All right. So now, once again, we fix it up with our so JA This is JA, and this is JB. The second one is JB. So JA equal output B. So let me just put the output and look. All right, so simulate the circuit. All right, so we'll put our circuit together. JA equal B. So this I'm going to connect to B. KA is B bar, so I'm going to connect KA B bar. JB equal A. KB equal A bar. Sure. Oh, bad example. The reason why this is a bad example is because I wanted to show how you incorporate I into the circuit. But this circuit here don't need the input I, which is very strange. Which means that we do something wrong somewhere in all of this. Check. So let us go back through the thing here and see. Somebody who understand what we're doing can check on the table to make sure that it is.
Sir Fraser, Sir Fraser, for one, we have 111. What is KB? Is it 0 or X?
What is K?
KB, we have 111 in the present state.
Mm.
KB 0 or X?
KA should be X.
No, KB.
KB should be X.
Okay.
So KA should be X. What you have KA as? Should be X.
Yeah. I think that's one of the issues.
So let me just do that back over. Uh, so the KA now would be what now? XXX. 4 X's. 1 0 1 X. Again. Okay. Yeah, but the same thing. All right, somebody check through because it should involve I at some point. Let me check back through. First one, X 1 0 1. Simplify. Second one, did that already. Third one, XX 1 X 0 X 1 X. Okay. That's X 1 X 0 X 1 X. Alright, let me just check back through. 0, when I is 0, we 0 don't care. 1 goes to 2, 2 goes to 3, 3 goes to 1, 0 goes to 1, 1 goes to 0, 2 goes to 1, 0 to 1. Just check back with me here now. If you have 0 to 1, what is that in the characteristic?
1x, yeah.
1 to 1,
x0.
x0,
Yeah.
1 to 1,
Yes, sir. Yes, sir.
0x. 1 to 0. What is 1 to 0?
1.
So I tell you what is 1 to 0 and the
X1.
x1, 1 to 0.
Yes, sir.
1x. Change that. 0 to 1.
One XM.
Change that to 0 to 0.
0x.
But that's 0x.
Yeah.
Everything 1 to 0.
X1.
All right. So what changes there? B 1 to 0.
X1.
0 to 1.
1x.
1 to 1.
X0.
0 to 0.
6.
0 to 0.
0x.
0x. 1 to 0.
X1.
0 to 1.
1x.
All right. So I'm going to go back J and K. J the first flip flop. So JA now is X 1 XX 1 0 XX. Okay. So that is not I. You must say A is I plus not C. And KA that's X 0 1 XX 1 X KA is C plus A, but C is B and A is I. What did I say JA was? We just rub it out and I don't remember. Yeah, let's go back over. JA was X1 XX 1 0 XX. That's X. Go again. X1 XX 1 0 XX. I bar plus B bar. All right, so we'd have to change our circuit. So it has JA. So this would be what our values are now. So if you go back to the next screen, it will be JA is equal to I bar plus B bar. KA is I plus B. JB is A and KB is A bar. Right, so those would be what we need to put into the circuit. All right, so now we go back. So our circuit would have two flip-flops. We would have our clock. You have to ground it. So we need the input I. You can do the input I two different ways. You can use battery, or you can use the VCC supply. And then now we need a switch. And so this thing up here says space. So when you touch the space bar, it's supposed to change, right? You can change it to if you touch I. So would have a V, and then would need to ground it as well. So KA is I. Oh, sorry. K is I plus B. We need to put that through an OR gate. And J is not I plus not B. So we use a little bit of Boolean logic. Anybody can simplify not I plus not B. De Morgan's law. Again, not talking to myself, right? Right. So I, not I, and not I plus not B is under De Morgan's law. The plus turns to time, says I dot B not the whole entire thing. So therefore, we are going to pass each of these through a NAND gate. So passing B and I to a NAND gate. All right. JB is the output A. So this is JB is output O. The output A, and KB is the output, not A. We can connect this. Where we put the clock. All right, so basically you get the gist of what it is that we are doing. All right, so we have our input, which is I, the first gate. We have to connect everything to the clock. If you're simulating, then you have to change the frequency so that you can actually see what's going on. right? 1 or 2 hertz. All right, so this would be the setup that we would have for the circuit. All right, so the plan is to go for 2 hours and then what time can we meet on Friday? Earlier, if possible.
Same time, Friday, sir.
Huh? They canceled the next class that I have because of lack of students, the few students. So they said that they must put the persons on independent subject, which don't make no sense because it's the same thing. Anyway, trying to what I discuss with them.
Sir, about around 12, 1 o'clock. Is that okay?
If that would be all right with everybody else.